Hey guys, in this particular video, I'm going to show you how to calculate the work done in order to lift a ball up a distance h from the ground. Alright, so let's say we've got a ball just here, and let's say that at some point we decide to lift that ball up, say, a distance h from the ground. So it was on the ground, and then we decide to lift it up to this distance right here and hold it there. So this is our hand, and we've lifted it up, right? So that's our hand, right there. Alright, so in order to figure out the work done by us in lifting this ball up this distance h, and let me just draw that to make that really clear. We've lifted up a distance h from the ground. We need to figure out what are the forces acting on this ball mid-flight. And we can do that quite easily. We know that if we draw a free body diagram, the forces on this ball will be the force I'm applying to it, which will be a force acting up on this ball through its center of mass, and I'll just call that force we're applying to it F me. And this could be changing in time. We don't know. It could vary depending on how we want to lift the ball. But the force due to gravity will remain constant and acting downwards with a magnitude of mg. Right? Alright, well, given that this is a free body diagram and these are the only two forces acting on this ball and neglecting friction, how do we apply this to our formula? Our change in mechanical energy is equal to our work done by non-conservative forces. Well, the first thing to realize is the force we're applying on the ball is a non-conservative force, right? I mean, if it's not gravity, it's not our elastic energy, so it must be non-conservative, and more importantly, it's path dependent, right? So our total work done by non-conservative forces in this case will just be the total work done by me, because the only non-conservative force in this example is the force I'm applying to the ball, right? What about mg? Why isn't that a non-conservative force? Well, because in a previous video I've proved that it is a conservative force. It's actually included in this term just here. So let me write this down on the left-hand side, leaving it unchanged for now. I don't want to skip too many steps. This will be the left-hand side is the change in mechanical energy is going to be the work done by non-conservative forces, which is the work done by me, right? So if I scroll down a little bit more, I can actually rewrite the change in mechanical energy as the change in kinetic energy plus the change in potential energy, which can also be written as the change in gravitational potential energy, sometimes denoted as U, plus the change in elastic energy. And that's going to be equal to the work done by me. Work done by me. Alright, well, first of all, we need to realize that this term gets eliminated to 0 because there's no springs involved here whatsoever, right? Or stretching of any kind. Alright, and now we need to expand this side out. Well, what's our change in kinetic energy? Well, under the assumption that I've lifted this ball up from rest and I leave it hovering on my hand at rest, that means at our final velocity we're going to have v2 is equal to 0, right? And v1 is equal to 0, right? And you can work that out too, but it essentially means that our change in kinetic energy is going to be 1/2 m times v2 squared minus v1 squared, which is going to be equal to 1/2 m times 0 squared minus 0 squared, right? Which is just going to be equal to 0. In other words, there's no change in kinetic energy. The ball hasn't sped up or slowed down at all, right? So essentially, that means that this term is going to be equal to 0 because the velocities are the same at the start as they were at the beginning, as they were at the end. Alright, so that would imply then that your change in gravitational potential energy is going to be equal to the work done by me, right? Whatever this is, right? And we know that our change in gravitational potential energy is just mg times by h2 minus h1, or y2 minus y1. Both are fine, but I'll write it as y2 minus y1 because that's what most textbooks use. Is going to be equal to the work done by me, right? Well, depending on where we place our coordinate system, we'll find that y2 minus y1 is equal to h, and just to prove that, let me just choose a coordinate system, I don't know, let's place it here, right? In which case, let me scroll down a bit, in which case y2 is going to be equal to 0, and y1 is going to be equal to negative h, right? Right, so if basically, I may be rushing through this a little bit, let me slow down. This is y, this is x. y2 is going to be equal to 0, because that's where I've placed my axis. y1 is going to be negative h, because it's lower than the origin by a distance h. Right, so if we substitute these values in, we're going to get mg times y2, which is 0, based off where I defined my axis to be, minus, and what's y1? Negative h, right? And that's going to be equal to the work done by me. Right? And if you simplify that out, we can say that the work that I've done to move the ball a distance h against gravity is going to be equal to, in magnitude, ngh. Alright? So that's the work I've done in order to lift the ball up against gravity. Right? And it's quite interesting to notice that it's exactly equal in magnitude to the work done against gravity, or like the work done that it would take to move this ball downwards a distance h, right? And I've always found that kind of fascinating, actually. Because what that's essentially saying is, if I'm doing work to move this ball up, that means gravity is doing negative work to move the ball up. Likewise, if I were to drop this ball back down, say I were to move my hand and drop this ball down, gravity would be doing positive work, and I would be doing negative work. I hope that makes sense, guys. This is like a kind of formal proof into saying, into this well-known type of phenomenon.